will begin this talk with Eunice. She is a professor at Cornell University in the Chemistry and Chemical Engineering departments. If you can share your screen, Professor Bay. So yeah, Eunice obtained her bachelor's in chemistry at UC Berkeley and PhD in chemistry at Northwestern University. And then she spent 3 years at postdoctoral research at Columbia University before joining the department at Cornell University as a professor. Her research is about understanding and controlling spin interactions using light, and she's going to talk to us a bit about that in her presentation, Magnon-Excitation or Exciton and Magnon-Photon Couplings. So with that, I will hand it over to you, Professor Bay.
Right. Thank you, Galen. Thanks everyone for attending my talk and organizing this seminar. I've actually never heard about this seminar series, and I was pretty surprised that it's going on for 24 hours. Hopefully people are awake still. Okay, so today I'm going to talk about Magnon-Exciton and Magnon-Photon couplings. And I think it's been a while since I gave a Zoom talk. Personally, I think it's a bit weird if I'm just constantly talking. So if you have any questions, just feel free to ask me questions in the chat. I'll keep checking on the chat, or you can, I don't know if you can just talk also, but if you can, you can also just stop me. All right, so as Galen mentioned, that most of my backgrounds are in chemistry, but starting my postdoc, somehow I got into condensed matter physics, and nowadays I think I'm half and half. To kind of demonstrate that, I want to start with this half and half kind of picture. So when we think about coupling in chemistry, a lot of chemistry students will think about bonding. So here on the left side, I have a picture of carbon-carbon atoms which have exact same energy, and then here we're looking at the p orbitals, and we know that these orbitals can symmetrically interact, forming the bonding interactions, or they can have anti-symmetric interaction, forming a anti-bonding interactions. And note that the carbon atoms here, we're really just talking about the resonant coupling, and we can mathematically write down this resonant coupling using the simple Hamiltonian 2x2 matrix, and then we have the energy of two systems, for example, carbon, then the energy of A and B will be exactly the same. And then these off-diagonal elements will quantify how much the overlap there is and how strong the coupling between the two is. So depending on the V, we can have very, very large hybridized states, or we can have a small hybridized state. So most of the time when we talk about couplings, this is the picture. But there's a problem when we have two things that have very, very different energy scales. So for example, excitons and magnons have drastically different energy scales. So we know that excitons, they live in semiconductors. We can photoexcite the valence band. Then we can create this electron-hole pair. And usually their energy scales is in electron volts. And we have magnets, and we can imagine flipping a spin from ground state to this excited state. And for magnons, this is like just having one spin flipped in these connected spin configuration is very energetically not favorable. So what ends up happening is that this flip angle is shared among their neighbors. So it ends up creating this collective oscillation, which we call spin wave. And then the quantized energy of the spin wave is magnon, and their energy scales is about 4 orders of magnitude smaller than the exciton. So there's a question about how can we couple these two things, and we no longer can apply the resonant coupling energy scales we just talked about. And before we start thinking about this question, we want to motivate, like, why do we even care about coupling the two to begin with? And there's twofold reasons. One is fundamental reasons. And historically, we've seen that when two things are coupled, we saw a new physical phenomena emerging from that. So one, I think, classical example is a Jahn-Teller distortion. And you see the octahedral cluster, and when this axial position is elongated, what we see is not just a structural change, but also the stabilization of the electronic structure. The T2G level is now stabilized because of this axial elongation. And this is really coming from the electron-photon coupling. And when we have strong spin orbit coupling systems, we've also seen the spin Hall effect, where the spin and up and down can split when we apply the current to the system. So as we've seen, fundamentally, that when two very, very different things are coupled, a new phenomena could emerge from that. So there's a fundamental motivation behind studying the magnons and exciton coupling. And practically also, when two things are coupled, then we can imagine using one to control the other. So for example, usually how people control excitons is by using electric field or gating or chemical doping, or nowadays with 2D materials, we can imagine creating a heterostructures. But if we have a magnon-exciton coupling, then we can start to add magnons to this list of things that we can control excitons. And additionally, traditionally people would use like temperature gradient, field, or microwave cavity, strains, these things to control magnons. But when we have exciton coupled magnons, then we can start to think about using excitons to manipulate magnons however we want. So excitons and magnons themselves have a lot of interesting applications, and having this extra control knob essentially give us more easy access to controlling one or the other using them. All right, so for those reasons, we want to study how the magnons and excitons, which have very, very different energy scales, how they couple together. All right, so the system that we're going to look at today is a two-dimensional material. It's like a graphene material. So we can like use a Scotch tape to exfoliate these materials, and you can see that they have the van der Waals interactions between the layers. But the properties that I'm going to talk about, I think it's not so important that we have a 2D material, but what's really important is that we need to have an intrinsically magnetic and also a semiconducting material. So if we look at the magnetic structure of chromium sulfur bromide, each layer, so if we have monolayer, is ferromagnetically coupled. But if we have bilayers or odd number of layers, we'll have antiferromagnetically coupled system. And if we look at their electronic properties, here we're looking at the band gap is about 1.5 eV. And then from photoluminescence measurement, we can quantify their exciton energy. And you can see that the binding energy of the exciton is pretty large. And if we look at the band structure, this is the band structures calculated by Ting's group in University of Washington. And it's really interesting. So initially, we talked about bonding, and the bonding geometry is highly relevant when we start looking at the band structure. So if we look at the conduction band, you see that along the gamma to y direction is very, very dispersive, but gamma to x direction is quite flat. And then if you look at the geometry, the crystal structure geometry, and then look at the participating bonding orbitals to the conduction band, we can actually kind of reason out why it's so flat along the gamma to x direction. And that's because the orbital overlap there is quite limited because of the geometry, the angle is really not favorable. But if we look at gamma to y directions, the orbital overlap can be quite enhanced. And so along that direction, we see this rather dispersive. So if you look at the energy scale, it is quite dispersive along that direction. And because of that, what we see is that the exciton structure in real space is quite delocalized along the b-axis where we saw the dispersive band structure. So here we're looking at hole that's fixed in the middle, that's the green. And then we're seeing the electron density of the exciton, so this electron and hole pair. And you see that the density is more delocalized along the b-axis compared to the a-axis. And this is about like 20 unit cells it's delocalized over. And because of this property, we also see optically that if we have a linearly polarized light along the dispersive direction, then there's a strong absorption and emission. But if we polarize along the other direction, then there's essentially no absorption and no emission. So we can see a very anisotropic electronic response from this the band structure. All right, so because it's both magnetic and semiconductor, we can easily measure the exciton property just by measuring photoluminescence. So y-axis here is looking at the energy scale of the exciton. So this is, if we do the cut, then the spectrum will look like this. And if we apply magnetic field along b-axis, but even if we apply along a or c-axis, what we would see is just a flat. So the peak is not changing with applied field. But if we do that in bilayer, so the difference between this is a monolayer and bilayer. So monolayer is just ferromagnetic versus bilayer is antiferromagnetic. So here, when we have a bilayer system, if we saturate the spin so that it's ferromagnetic, what we read here is that the exciton energy changed about 20 MeV. And here we're applying field along the easy axis and the intermediate and hard axis. And you can see that as long as we create ferromagnetic state, their exciton energies are same, but depending on the direction, we would see the flop or flip behavior. And this really gives us an easy way to read out the spin structure. So let's say we know where the direction of the magnetic field is, and if we read just the exciton energy, the peak value, then we would just know what the spin canting angle of the system is. So this, and then the reason why that we would see this lowering of the exciton energy in real space picture, you can visualize that in the antiferromagnetic state, the electron and hole are spin forbidden to hop to the next layer. But when we have ferromagnetic state, the electron density and both hole, though we fix it here, can essentially tunnel to the next layer. So in this picture, you can imagine that when both layers are pointing the same direction for spin, then you can imagine that their conduction and valence band become hybridized, just like the carbon-carbon atoms. And it's both the electronic structure and also the exciton binding energy that changes with the spin, and their effect kind of cancels out. So if you just look at the band structure hybridization, it will be about like 0.1 EV stabilization, but because of the binding energy, it cancels out. And at the end, we will see about 20 MeV change. And this theory work is done by Ting, and then the experiment work is done in my postdoc group, Xiaoyang's group, and Xiaodong's group in collaboration with the two group. So this is the spin exciton coupling picture in chromium sulfur bromide, and we're just dealing with the static spins. And so the next question is, we're interested in how the magnons are coupled to the excitons. And it's quite simple. We can imagine that we understand this picture pretty well because of the static spin and exciton coupling. And then we can start drawing the cartoons for how the magnon would look like. So here I'm just drawing a cartoon of the spin oscillations of the in-phase motion. So you can see that at certain times, the canting angle becomes larger between the two layers. So you can imagine the top is layer 2, and then the bottom is layer 1. And you see that over time, when we launch spin wave, that these will precess in phase. Is one of the mode is in phase. And you can see that their canting angle changes. And already from this simple cartoon picture, you could anticipate the exciton energy at different time delays, or at time points, like we say T1, T2, T3, you can already imagine that when we launch a spin wave in the system, the exciton energy will be modulated in time. And here we're looking at the magnetic anisotropy. So in earlier slides, I already talked about that we have 3 axes, the easy axis, intermediate axis, and hard axis. And because of this anisotropy, even at zero magnetic field, we will have 2 non-degenerate modes, in phase and out of phase. And these will be determined by the anisotropy values, AX, AY, and AC, and also the interlayer coupling between the 2 layers. And so you would kind of anticipate the interlayer coupling is quite weak because of the van der Waals interactions. And so if we look at the frequency, most of it is contributed by the anisotropy values. All right, so because of the triaxial anisotropy, depending on where you apply the magnetic field, you would see two branch behaving differently with respect to the magnetic field. And the field direction that we apply for optical measurement is along the hard axis, and then you can see that that out of phase and then in phase modes both decreases with the external magnetic field. And as I already alluded in earlier slides, that when we have spin precession, particularly in chromium sulfur bromide, because of the spin exciton coupling, what we expect is the exciton energy at each of these time points will change in over time. And being able to measure this is actually quite simple if we use time-resolved optical measurement. So you can imagine that we create a coherent oscillation of spin wave. So the phase needs to be well defined. And what will happen is that, let's say in steady state, we have this exciton peak at time 0. And this peak will oscillate at the frequency of spin wave if our picture is correct. And this is the experiment that I did when I was a postdoc in Chaoyang's group at Columbia. And here you can really see these nice oscillations coming from, these are the excitonic peaks that we collect in steady state without any pump. And you can imagine that this pump pulse is acting as an impulse, and then that launches the coherent spin waves in the CrSBr. And these peaks are oscillating at the frequency of the spin wave. So if we take the Fourier transform, then we see exactly the frequencies that we expect from microwave measurement. So in microwave measurement, we would sweep between about 1 to 40 gigahertz, and we'll see the resonance peak. But in optical measurement, we're essentially probing how the exciton energy is being modulated with time. And that is how we're measuring the Magnon, the coherent spin wave in our system by monitoring the exciton energy shift. And the reason why we know that this peak is shifting is because of this phase flip. And so the way we collect this is we take the delta of pump on and pump off. And so exactly at the peak, we would see no signal, and around it is where we see the most signal. So that's why there's a phase flip around the peak. All right, and then we can quantify the amount of exciton energy that's being shifted by Magnon, and it's quite nice because then we can calculate the angle, the precession angle from this exciton energy shift. And here we see that the Magnon energy is about 0.1 milli-electron volts. So it's a very small energy, and if they're completely decoupled, then at most it can induce about 0.1 MeV change. But because of their coupling, what we see is that this very low energy Magnon can induce about 40 to 50 times larger energy shift in excitons. And we can quantify that for bulk system and then down to a few layer system. I think the signal to noise was not so good for bilayer. But we can still measure the frequency down to the bilayer, and then you can see that they're mostly the same all at different number of layers. And what's important is that we can do this measurement, the exciton sensing measurement, to look at the spin dynamics down to bilayer, because we are only sensitive to the interlayer coupling. So if we have monolayer system, we won't be able to track the system like we did before. All right, so this is the picture of the static spin and exciton coupling, and then this is the picture for Magnon and exciton. So essentially what got changed was this time dynamics, that this static spin picture is really the foundation of the Magnon exciton coupling that we were seeing. And using this fairly simple way to measure the spin wave dynamics, what we also do is, instead of just overlapping pump and probe beam at the same spot, we can essentially scan the probe beam around the pump to see the propagation of the spin wave. And so we placed the probe beam along several different positions. And you can see that when we place our probe beam exactly at the pump spot, we will see the wave generating instantaneously as we excite. But if we move the probe further away, it takes for the waves that were generated at the pump spot to get to that spot. So what we see is that it takes like there's no signal, and then like start to see a signal from the exciton energy being modulated. And so in using this technique, we can essentially see like how are the spin waves in our systems propagating in space and time. And if we look at their coherence time and the group velocities, they're not too bad. So especially the coherence length and time. I would say it's not as good as like conventional magnetic systems like YIG, but for 2D material compared to other 2D material, I think it's not too bad. All right, so using this external sensing method, I think my collaborators in Chadong's group, Jeff and Yafi, did some follow-up work. And then here we use the exact same method, the external sensing method. And here what they show is that by applying the magnetic field along at an angle direction, and that can induce the magnon-magnon coupling by breaking the symmetry. And they were able to observe that these dark and bright mode, these are the in-phase and out-of-phase modes, can become hybridized, and then it can become bright mode. But if you're interested, I recommend reading this paper. It's a very neat work. Okay, so that was all about external sensing, like how are we doing external sensing for monitoring the spin dynamics in CrSBr. And I think I find it really interesting, and I think a lot of people in the community find it interesting. And so we start to ask ourselves, like, can we make this like a universal phenomenon in other system? And so we were thinking about like, are there any other 2D magnetic systems that have this A-type or antiferromagnetic structures that would have this kind of spin external coupling? So we were starting to ask ourselves, like, what is the property in CrSBr that gives us these very nice experimental signatures? And so this is the work that I started doing in my independent group at Cornell. And so we were doing some literature work. This is when I just started and we didn't have a lab. And so we just like sit down and like read papers together. And then, so this is a paper that were published a few years ago. And then we were looking at how their PL emission change with external magnetic field. So this is chromium triiodide. And you see that no matter what field, whether it's ferromagnetic, antiferromagnetic, the peak position does not change. So it's about 1.1 eV. The relative amplitude, depending on how we excite with the circularly polarized light, but the peak position was not changing. And also for nickel PS3 systems, we saw very tiny shift. This is the external energy versus magnetic field. And we saw very, very tiny shift at a huge magnetic field. And the reason for this is because it's an intra-layer antiferromagnetic system. So to flip the spins, you would need a lot more field. And so you see that at most, we are seeing about 1 MeV change when we apply this huge amount of magnetic field. And then next thing is we were looking at the band structures. And what we noticed was that their band structure was rather flat. So here you see the energy scale. We're looking at about like 2 to 3 energy scale, but here it's at most like 0.3. So you see like the bands are quite flat, and then if you look at the geometry of the bonding, we would see that the ligand to metal energy was not as resonant, and also the geometry prevent them to have a more bonding interaction. So there's essentially less dispersion in the band structures. And then Ting also calculated the real space size of the excitons for chromium triiodide, and then this was estimated from experimental work, and you would see that their exciton size is much smaller, about like 100 times smaller than chromium sulfur bromide. So then we really understood that we would need to have not only just a magnetic semiconducting system, but also what we need is a highly dispersive band or highly delocalized excitons to be able to have this kind of spin exciton coupling that we were really excited about for chromium sulfur bromide. All right. So part one, if we summarize it, we saw that the delocalized exciton is essential for spin exciton coupling, and exciton is a really good sensor that is sensitive to measuring the spin environment. But there were some limitations with optical experiments. So we wanted to mostly see the Magnon-Exciton coupling themselves, but when we use optical excitation, it would create like phonons, excitons, and magnons all at once, and so it's difficult to track essentially the quasi-particle numbers. And so we wanted to really push the limit of the exciton sensing method, and so optical excitation was kind of limiting. So to bypass that, I was starting to think about coupling the magnons to microwave photons. Then we should be able to easily control the number of magnons generated in the systems using the microwave powers. And so in my view, my picture of Magnon-Photon coupling was just two harmonic oscillators that are coupled, like two pendulums coupled with a spring. But turns out there's also another type of coupling. It was new to me that there was a whole field of cavity magnonics, and I think it's been studied quite extensively. And I've also learned about the dissipative coupling. So there's no coherent energy exchange between the two modes, but they essentially share the bath together. And depending on the system and the bath interactions, the mode can essentially collapse at these exceptional points for the exactly at the resonant frequency for the two modes. But anyway, so I was really interested that there was already a whole field of cavity magnonics, so people already know how to manipulate magnons really well with microwaves, and there was all kinds of coupling and types like Hermitian, like non-Hermitian physics there. And so, and then also there's beyond that, there's also interest in quantum cavity magnonics. So all of this phenomena that I just talked about here can be described semi-classically, but really moving to the quantum region, people are thinking about like creating an entanglement state between the qubit and magnon mode. And also being able to read out a single magnon using qubit. And so all of this, like there's several motivations. Like for me, my motivation was being able to just generate magnons in the system without having to worry about all these other systems. And there's also this existing field of cavity magnonics and quantum magnonics. And so our group start working on how can we essentially bring in new aspect by incorporating the 2D magnets, the chromium sulfur bromide that we're studying to this whole field, and also address the question that I had with my experiment condition. And so we start thinking about how can we incorporate this, and of course we were not the first people to think about this, and we found out that pretty recently that another group has also worked on coupling the 2D magnets to microwave cavity. So long story short, we also start working on it. Jia Cheng is a postdoc in my group who start working on it. And we were also able to demonstrate the coherent coupling. So here the picture is similar to the carbon-carbon bond that we talked about. And based on from here, we're also interested in implementing the optical experiments that we already know how to do well. All right, so I'm running out of time. So to summarize, I talked a lot about Magnon-Exciton coupling, and then also the Magnon-Photon coupling that we recently achieved. And there's a lot of interesting follow-up work that we're working on. And we also have a positions in our group. So if you're interested in this kind of work, feel free to reach out to me. Okay, so thanks everyone, and sorry I went over like 2 minutes, so feel free to ask me any questions.
Oh, sorry. you actually still have about 3 minutes, but
Oh,
or 4
wait, is
minutes or
this
so.
not including the question and...
Yeah, sorry, that's my bad. I accidentally stopped
Oh,
the
okay, okay, I see.
timer and then I restarted to include the, yeah.
Oh, okay. Yeah, no worries, but we have plenty of time for
Yeah.
questions then. Yeah.
Yes, exactly. So yeah. So yeah, thank you to the speaker for this very nice talk. You can clap if you like in the Zoom world. Um, yeah, so if you have any questions, you can feel free to type them in the chat or just raise your hand and we will call on you. Hold on, let me just pull up participants so I can see if hands are raised. Okay, so maybe I'll just start the question session here. So I guess relating to part one, maybe this was just with some of the cartoons, but it
Mhm.
appears like when you have the two layers, you get this sort of lag in the phase lag between the magnons in each layer. Does this result in sort of a more broad peak in the exciton energy? And is that something you try to minimize?
Why? Oh, the way I drew the cartoon, it looks like there's a lag. But there shouldn't be a lag. The two layers
Okay, so there
being...
is no.
Yeah. I think it's my bad drawing, but there shouldn't be a lag. And they would precess together. Yeah.
And so I'm wondering too, also if you introduce any sort of intermediate layer between these two layers to tune the coupling at all? Have you tried something like this?
Intermediate layers. Yeah, so people have like applied pressure to change the interlayer coupling, so you can like make them squished, or like the natural will be like this, and then applying pressure will make it the distance to be short. Yeah, so that in that way people can tune the interlayer coupling.
Okay,
Is that your question?
interesting. Yes, yeah, that answers
Yeah,
it.
yeah.
Okay, so we have one question in the chat, and then I also see Alexander is raising his hand. So Alexander B will, if you would like to unmute, and maybe.
Yeah, sure. Hi.
Yeah.
Hello.
Hi. So I'm a undergraduate at Oregon State, and we do some research on CRISPR as well, with the pump probe. And so I sort of had a question about one phenomena that I've seen in the lab that's been kind of confusing is sometimes when the pump and the probe lines are overlapped on the sample, we get much worse signal yield. I was wondering if that's something that you'd expect in a system like CRISPR, or if that could be caused by um, some other things going on in the lab.
That's weird. So in my paper, in the supporting information, if you see closely, there is a power dependent result. So I think you want to first identify, like, are you in the linear regime? So when I say linear regime, you would see that as you increase the pump power, the dr over r will also increase. And if you're in that linear regime, you should also see increasing trend for magnons. But if you're beyond that region, I don't know, because we mostly try to be in the linear region, so the picture is a bit easier and simpler. So maybe you wanna do some power dependence and then identify, like, are you in the linear regime or are you already like beyond that?
Okay. Great, thank you.
Yeah.
So we have a question in the chat from John Fullerton. So he says, do you expect any different effects for the excitons if you use other materials from the chromium halides? So for example, like chromium bromium 3 or chromium chlorine 3.
Yeah, so I think the BR3 and CL3, those are very similar to the triiodide system that I talked about. So I think if you were to try to do the same measurement, like, you essentially would not see the effect that I discussed, because the exciton is so localized. Essentially, they don't care like what the spin environment around it is. So that's why in chromium triiodide system, whether you apply like 1 Tesla or -1 Tesla to make ferromagnetic state point in different directions, like you wouldn't see any change in the exciton energy. So the way people detect like coherent spin waves in these systems, they were using a traditional method of like time resolved MOC. So there are papers discussing this. I think was chromium triiodide. But I haven't seen the BR3 or CL3, but I think I would expect them to have similar effect.
Okay, if anybody else has questions, please feel free to put them in the chat or raise your hand. We still have some time. In the meantime, maybe I can ask. So yeah, sorry again for maybe confusing with the time. I'm just wondering if you can talk a little bit more about the sort of application side of these things. So sort of how you go from your research into putting these in the spintronic devices and further
Yeah.
applications.
So that was also part of this this talk. Yeah, so we were really interested in the transduction. So we want to be able to read out so this is the result. So we know that our system has Magnon-Exciton coupling. So that means that if we have a Magnon in the system, we can easily optically read those out. And so we're trying to couple the Magnons to microwave photons. And the goal is like, let's say we insert like hundreds or thousands of microwave photons in the system, like, are we going to be able to optically read out? Then in that sense, we're transducing the microwave photons to optical photons. So we're interested in doing transduction in a different way that people have been doing in the community. So most people haven't had this Magnon-Exciton coupling because the phenomena itself is relatively new, like it's published in 2022. So we're trying to use this kind of new coupling to realize like perhaps we could think about enhancing the microwave to optical transduction efficiency. Yeah, so those are the directions that we're interested in.
Yeah. Okay. Yes, thank you very much. And then you also touched a little bit on the quantum cavity magnonics. Is there any sort of application you see from the Magnon-Exciton couplings for quantum magnonics?
Yeah. So most of the quantum magnonic studies have been using the superconducting qubit. But when we're dealing with magnons, I think it's also natural to think about spin. Like we can easily couple magnons to other spin-based qubits. So those are also the direction that we're thinking. And also, right now, the qubit provides the strongest nonlinear interactions in the quantum magnonics, and we are hoping that like essentially do we always need to have that superconducting qubit to reach the quantum magnonic state? Is the kind of big and open-ended question that we're also tackling right now. So without qubit, it's really difficult to even generate single magnons. And we're thinking about like how can we get rid of the qubit part and still be able to operate in quantum magnon state. Yeah.
And it looks like we have a couple follow-up questions in the chat. So one from Graham, he says, could you explain again the Magnon-Exciton coupling?
I think then I would have to give another talk. So that was part one. I guess what aspect did you not understand? Maybe you could.
Yeah, so he says later in the chat, basically as in its physical origin.
Okay. So the physical origin is the spin-exciton coupling, which was the very beginning. So I think this is probably the simplest way. So the spin-exciton coupling is the origin of Magnon-Exciton coupling. Yeah.
Okay, and then we have one more question here from Olivia Zanoni. So she says, do you expect that this interesting behavior would somehow extend into thin films, or is it confined only to 2D materials?
Yeah, this is a great question. So I think, yeah, I think it's difficult to like I've talked to a lot of like synthetic material chemists or material scientists, and turns out it's really difficult to like synthesize another bulk system that would have the exact same property as chromium sulfur bromide. So yeah, I'm also wondering if like people in the past have studied, or even now like study the synthetic antiferromagnetic systems a lot. But I think in the past, like it's been studied mostly in the magnetic property or magnetic structure focused. But if there's a way to like create a synthetic antiferromagnets with a similar electronic structure that we want, just based on the chromium sulfur bromide work, I think that would be really interesting directions. And in that way, like we can also think about like scalability, and more tunability. Yeah, so in that sense, I think 2D magnets, like in the community, people are also like thinking about creating heterostructures. I think there are several like theoretical works predicting that if we heterostack chromium sulfur bromide in the right geometry and orientation, like we could imagine creating like alter magnets as well. So I think there are many like synthetic ways to achieve this, but I think it's challenging to know what's the best approach.
Yeah, so thank you for your answer, and thank you, Olivia, for that question. Oh, maybe we have, oh yeah, she says thank you as well. Yeah, this is also something I was curious about as someone who works with thin films rather than 2D materials. So thank you very much. Okay, so let's thank the speaker one more time.